All right. I'll start now. So last time we have discussed the concept of looking for new physics at intensity frontier, light very weakly coupled particles. I've told you, we formulated the general kind of portal ideas of how we can couple light new states to the standard model, and I've discussed a little bit things related to the standard model via the Higgs portal, although not extensively, and gave you the statement that I think that right-handed neutrinos are the prime candidates for the particles in the dark sector. Because, with them we have the best or easiest explanation for the phenomena we see, neutrino oscillations mixing. Now I would go to the case number 2, and that is axions motivated by something we don't see. And we don't see a lot of CP violation in the strong QCD sector, although in the mid-70s, people realized that there should be some ways of breaking CP in QCD. And that's the axions are sort of called for as the most natural universal solution to the strong CP problem. Okay, so this subject is really enormous, especially if I go into details of that topic. So what I decided to do, I would give you first kind of the executive summary for 20 minutes of what everyone, every theoretical physicist really should know about the topic, and then go to some details, and suspected phenomenology will be postponed to the next lecture. We'll see how it goes. So basically, quantum chromodynamics, and more generically standard model, has a non-trivial vacuum structure. Related to SU3 color dynamics and instantons. We believe that instantons are responsible for making masses of the singlet mesons. If you talk about the two flavors, it would be eta. In 3 flavors, it would be eta prime, to be much larger than the masses of pions or eta. So this parametrically larger, right? So if when you send MQ to 0, this part goes to 0. This stays finite. This is something known as the explanation of the naive expectation would be that this is on the order of this, and known as the U1 problem. So same condition, the large mass of eta prime makes theta parameter in principle physical. Theta is introduced as an extra term to normal QCD Lagrangian, where we add g squared over 32 pi squared theta g mu nu a g mu nu a dual. Don't need to give you the definitions of this. This is a dualized field strength. All right. In terms of the energy of the vacuum, it turns out to be theta dependent, and if we plot it, it basically has a periodic structure with the minimum being at 0 and 2 pi is a physical equivalent point. So around minimum vacuum energy is proportional to a constant times theta squared. All right. Vacuum energy is not really, I mean, it's observable in principle, but up to a number, right? I can always introduce a cosmological constant and cancel this. If that's the problem, it's not a problem, right? So the problem arises, but before we go here, there's one important thing that I want to emphasize. You could say, why wouldn't the vacuum energy look for this smallest point and always relax to 0? There is an important property called super selection. And let's take 2 points, theta 1, theta 2 here. Energy density at point theta 2 is larger than at theta 1. But if I take any physical amplitude between vacuum 1 and any gauge invariant operator, anything at all between theta 1 and theta 2, we get something times delta function of theta 1 minus theta 2. This is an extremely important property, one that you always have to keep in mind when you think about theta vacua. Yes, the non-zero theta is not a minimum of energy, but you can't move from there by any means, okay?
So all this is below about
it's a vacuum, so vacuum is at zero temperature by definition. It's a definition, if you like, yes. Any gauge invariant operator. We are going to derive that. So yes, that's important. Yes. Now, so what is the problem of having any theta? If we have any theta, then besides the CP conserving properties, such as the total energy density, we can have CP violating properties, such as electric dipole moments. Yes? At finite temperature as well. I don't think you can switch thetas here. No. All right. So, because you can always present finite temperature as a collection of particles at finite temperature, right? So this is not just a vacuum statement. You can have vacuum plus particles transitioning to vacuum plus other particles, right? Anyways, any theta. What's the problem? So the problem is that under the P and T transformation, the GG dual parameter, which has kind of morally E dot B properties, it's minus minus. So it violates both parity and time reversal. No surprise then that you should expect something induced for the electric dipole moment of the neutron. Electric dipole moment of the neutron, despite what popular press writes you, it's not the charge displacements within the neutron, right? And it's basically the coupling of the neutron spin to electric field. Okay, this coupling, the coefficient in front of it, is called the neutron electric dipole moment, and it's believed to be, according to calculations, on the order of 10 to the minus 16 centimeters times theta, and current bounds are at the level 3 times 10 to the minus 26 centimeters E, implying that theta is somewhere smaller than 10 to the minus 10. And the strong CP problem is the problem why I can choose one parameter to be order 1, yet it prefers to be 10 to the minus 10 from the data. We don't understand why. It's not the same as the, say, you cannot even argue entropically for it, right? In the sense that theta, I don't know, 10 minus 2 or 10 minus 3 doesn't threaten life in the universe. So you cannot say, "Oh, we'll exclude it entropically." So that's a why question about the dimensionless parameters in the Lagrangian are called the naturalness problem, right? Or sometimes about dimensionful as well. So this is a naturalness problem. Okay. So the basically universal solution, and the only universal solution known, that is, start from any value of theta, and you can solve this problem by transforming QCD plus theta to QCD plus theta plus A, where A is the new light scalar field that has the following property. So we have kinetic term plus, here's my theta term, and I add A over FA, G dual, G squared over 32 pi squared. Now the vacuum energy is a function of theta plus A over FA, and the round minimum, it's proportional to some number times theta minus A over FA squared.
So I'm a bit confused. That was not a field there, right?
That is a parameter. As a parameter. And I keep this parameter here.
Right, but then why would it ever scan? Like, why are we talking about different E's for different data? It's just a parameter. So I mean, you can't.
It's a parameter, but you cannot go from one point to another. That's true. But just theoretically, you can calculate the energies, right? You can calculate in principle, observables as a function of theta. The same way as you can calculate observables as a functions of coupling constant, for example.
But you can't go from one to another.
You cannot go from one to another. No.
So it's true. Only when you are sticking into one equivalence class, there is a instance of yours you can opt for straight up.
it's true for the QCD, right? So if you don't have this picture, then you don't have the argument why the eta prime is massive. Okay, so as long as we make a eta prime massive, this picture is guaranteed.
Yeah, I agree with that.
Yeah.
But if I stick in instant count very different operator, then I have what transition from 0 to 5, there is none.
Well, these things I identify. Okay. Yeah.
Oh,
Yeah, I identify 0 into pi, right? So I'll have this slice if you like, right?
oh,
But yes, I agree that there could be subtleties. Now, around the minimum, we have this potential. So the minimum of this potential, now treat it, this vacuum energy as the effective potential for the axion field, which will immediately tell you that the vacuum value for the axion field would be minus Fa times theta. So we have the axion basically seeks the minimum of the potential. Strong CP solved this way because in all possible observables, theta will enter in the combination with the vacuum expectation value of A, and together they get they screen each other. Okay. If we go through the calculations, as I hope we will in this lecture, we will discover that the mass of the axion scales as mass of the quark to the power 1/2, lambda QCD to the power 3/2 divided by this parameter Fa. If you make quantitative inferences from the formulae we are going to derive, you'll get Ma equals to 6 millielectron volt. This is a small m here, times 10 to the 9 GeV over Fa. That by itself kind of all right. So this relation kind of implies for interesting choice of the parameters, I should say, implies the existence of very light particles, right? Possibly as light as the lightest neutrino's mass or lighter. All right. Axion potential. It's an effective model in the following sense. If we take axion field and draw a loop of gluons like that, we're going to end up with kinetic term correction to the mass of to the axion field, with some necessarily UV cutoff squared. Yes? I'll get to that in a second. So this is here you can take this is that allows to take any values of Fa, right? So it's just I've written in a suggestive way, right? That 10 to the 9 is some sort of good choice. Now, no, it's unrelated. I'll talk to that. So this is the corrections that you'd expect. Therefore, you'd need UV completion at some lambda UV on the order of Fa. These UV completions are known as Peccei-Quinn sectors that possess global U1 Peccei-Quinn symmetry that produces Goldstone boson A with the only non-derivative interaction A times G dual. So the phenomenology of axions it's a intensively researched subject, but in general you can sort of point out the most important features. This is a light particle in general, right? Even if I take Fa to a TV, it's still going to be a light particle. Then being light, it can be produced in the hot interiors of the stars and lead to the stellar energy loss. So if you talk to Georg Raffeld, he would lament endlessly by particle physicists using the word stellar cooling, because it's not cooling, except for supernovae it's cooling, but for all other stars it's heating, because then when the star loses energy, it contracts, and the more energetic nuclear reaction starts taking over, right? So stellar energy losses. Then if you have sources of axions, like the sun, core of the sun, you can hope on detecting it by using the axion photon conversion. Yes? Yes? Is it? Sorry, guys. Yeah. Yeah. No. So. All right, and among the other interesting phenomenology, there is, of course, initial displacement of axion field from equilibrium value, which stores energy. in coherent oscillation of a field which is morally equivalent to axion particles, and that is example of, how shall we call it, super cool dark matter, right? Because it sort of develops from from temperature zero state. Example of super cool dark matter. Previous cosmology speakers and dark matter guys probably have covered some of that stuff with you, no? The coherent oscillations of scalar field that can be treated as dark matter. Quickly, right. So, yes?
What is this equals to X7 are particles?
Particles, sorry.
So what is this initial?
Initially, you have the universe, then we have to put it in a historic context, right? So the initial state of the universe is a fairly rapid expansion, right? I mean, even if I forget about inflation, it's a rapid expansion at high temperatures, where the fact that there is a potential for the axion does not induce its motion, because it's Hubble damped. That is, the Hubble provides a friction that keeps this axion on the side of this potential. And then when it's allowed to move, it would start moving, and because there is very little dissipation, it starts rolling back and forth. If the universe, if it's not expanding, it just keep moving back and forth, but because of its expanding, the amplitude of this field redshifts as 1 over a to the power 3/2, leading to the cold dark matter kind of evolution with the scale as 1 of the radius of the universe cube. That's the simple thing. Yeah. Now the
Why is it super cool opposed to just regular cold dark matter? What makes it cold like super cool?
Oh, because it's initial dispersion in well, it depends a little bit, but if I had stick to this picture that it starts from the one and the same axion field throughout many horizon scales from some initial value, then it's has almost no velocity dispersion at all, as opposed to WIMPs that had being in full thermal contact with the standard model, right? So the intrinsic velocity dispersions of axions could be a lot less than for WIMPs, for example, right? Not crazy to suppose that.
But the dispersions today would be the same as for WIMPs.
Of course. This is a historic statement. Super cool, meaning that it was now it would be the same virialized dark matter as WIMPs, basically falling into gravitational wells created by itself, right? That's by overdensities. All right. So the last bit that I wanted to say here in the summary, that people often identify axion window. It slightly model dependent. But in general, this, if you kind of generous, you'd say that this FA scale is likely to be larger than this and smaller than 10 to the 12 GeV. Maybe this bound is far more robust. Below this, too much stellar energy loss. and here would be above this too much dark matter unless some tuning occurs in the initial displacement of this field. This is often called axion window.
So with tuning, can I go well above? Or
Yes, you can go well above, yes. This is a place where there was momentary excitement and de-excitement in connection with the BICEP 2 data, because if there would be a definitive proof that what BICEP saw was primordial, and there would be a large indication on large value of R, which translates to a large value of the Hubble scale during inflation, that would translate to the large fluctuations of the axion field on top of the, say, 10 to the 16 or the 10 to the 18 GeV, and that was disfavoring very large the kind of 10 to the 16 GeV range of this due to the isocurvature fluctuations stored in the axion field. So some people know the story, but okay.
Sorry, when SA is large, what is suppressing the dark matter density?
You say that I'm initially displaced from the bottom of the potential by a little bit, the 10 to the minus 3 compared to what I could be order 1, right? Not very satisfactory, but some people think that having FA on the scale of the grand unification is a more kind of desirable thing, because then you can probably tie it up to a more beautiful theoretical structure. And tuning of 10 minus 3, people say, whatever. All right. So
if you sort of higher in the potential, you have more dark matter.
That's right. Correct. Correct. So now the final word that I wanted to say in my introduction that took half the lecture, and that is ALPS. ALPS stands for axion like particles. So what is this? It's basically models with pseudoscalar A coupled derivatively to standard model via d mu A over FA times some operator. And the shift symmetry A to A plus a constant is violated only by ma squared a squared term which gives no interactions, right? I mean, there's no new vertices. This creates a technically natural model, but MA doesn't have to be equal to 1 over FA MQ 1/2 lambda 3 QCD 3/2. Could be larger or smaller. That's what people mean by when they say ALPS. Okay. I managed to cover all available quark. Yes.
So the origin of this mass term is.
All right. So now we are done with the introduction. We can discuss some of the interesting aspects of that. Okay. So flip them, right? All right. And as I expected, the summary took me half a lecture. So well, it's better this way than to get stuck at some technical detail and never give you the whole picture. Any general questions about this? There are probably lots of questions if you haven't seen much of that before, right? So let's now have a discussion of so this is going to be mostly qualitative discussion, except for one calculation that I want to make. All right. I want to spend 20 minutes or so on discussing the theta vacuum and why theta parameter is physical. As I just erased the formula that I would need. So we take lambda QCD plus theta g squared over 32 pi squared. These numbers are conventions here, right? You don't have to, in principle, take exactly that coefficient. And well, let's ask the question first: why is it at all giving us anything, right? I mean, so well, if I do in a QED, if I take if I do this QE, right, and erase A and A, what's going to happen? In QED, we are not bothered by adding F mu dual to the action. Why? It's a total derivative. Great. It's a total derivative. But guess what? In QCD, it's also a total derivative. That should give you creeps because, well, why don't we throw it away? This is the total derivative of the so-called Chern-Simons current. And let me write a definition of it here, although it's kind of painful. A nu d rho a sigma plus. We are not going to use it much in detail, but I'll just put it on the board. So it's a total derivative as well. The thing is, this is as in QED as well. This is not a gauge invariant current. So if I continue with d4x of this, to have any chance of this being something leading to non-physical to physical effects, I should have a possibility for the surface term not vanishing. So that is d4x times this coefficient. Let's just try it this way. And then basically I can rewrite it as the integral over the far distant surface and the flux of the Chern-Simons current through that surface, right? So let's take these surfaces as the surfaces at t minus infinity and t plus infinity. So we'll end up with theta g squared, 32 pi squared, and then the d3x of k0 at t plus infinity to k0 at t minus infinity. So if my vacuum that I could choose that minimizes the energy if vacuum values of a mu a are all equals to 0, then this surface, then the integral equals to 0, and I can throw it away. The big statement in QCD that this there are choices of a mu a that are pure gauges. That is, they don't create non-vanishing gluon fields, so they don't contribute to the energy density. But for them, the d3x of k0 not equal to 0, but equal to some what's called winding number. To visualize that, you can take an example of SU2 is easier to work with, and the gauge where A0 equals to 0. In that case, a configuration with non-zero winding number, for example, can be pictured as follows. So the AI configuration at x and t going to plus infinity, let's say, can be written as 1 over g u di u dagger di u. So you can recognize that this is a part of the gauge, basically pure gauge, with u of xi being the exponent of minus I pi xi sigma I over xi squared plus rho squared, where rho some parameter dimension of length. So if you calculate now the Chern-Simons boundary term for that field configuration, you'll get not a 0. Okay, you'll get not a 0. That proves you that you cannot throw away this term in the potential in a Lagrangian without thinking about it and worrying at all. Right? If you try to do the same for the U1 field, you will very quickly discover that that's just going to give you some trivial derivative of the scalar or scalar field, and it will give you a Chern-Simons 0 at both ends, and so you can throw it away in QED freely. You cannot do that so in QCD. Okay. Now, that is very suggestive that we should use the winding number that turns out to be integer as a label for different states with different values of Chern-Simons charge. So the A equals I equals 0 configuration, you can assign the winding number equals to 0. This configuration would correspond to the winding number equals to 1. Seem to be running out of chalk. And then you can then formally picture this is that we have gauge transformation and depends on u applied to this 0 winding number state. We get 1 and so on. You can have n state and transform it to n plus 1. Now, what does it mean? These are all pure gauges, so the energy of these configurations, if you like, are zeros. Okay, so it kind of invites a picture of potential wells, where this would be 1, 0, 1, 2, 3, and what this transformation does, it transforms you from one well to another, to another, to another. Okay, so now suppose that there is a infinite barrier between these wells and it going to plus infinity. Then the fact that there are separated wells do not matter at all, because you can sit in one well and the probability of quantum mechanical tunneling to the another, to the left or to the right, would be 0. Right? If action under the barrier going to infinity, tunneling rate going to 0, you can treat that as isolated vacuum, right? Yes?
So I understand the U1 you can put it away, but so if you go to the electroweak like at the SU2L, then you still...
This would be a situation where your heights of these barriers are very nearly infinite, right? Because the action under the barrier would be tiny. Okay, in the electroweak SU2, if that's what you're asking. So now the big thing, and what the instantons do. Instantons are finite action solutions with G mu non-zero that take you from one well to another. So in fact, we should be picturing basically multiple vacuum where instantons can generate physical transitions back and forth. Okay? The action of the instantons is proportional to 8 pi squared over G squared, but the G in the strong interaction regime it's a large parameter. So 8 pi squared over g squared is not a huge parameter, and therefore you can be assured that the instant-on fluctuations occur all the time. Now, what do we do in quantum mechanics where we have a set of equivalent energy wells where you can tunnel from one to another? If you have two wells, well, we know what to do. You take plus minus divide by square root of 2, right? That usually takes care of finding the energy eigenstates. So what you're doing here, what happens if you have an infinite series of them, like one-dimensional crystal? What do? Each well, from the point of view of the electrons that go around it, equivalent in terms of energetics, right? What do we do in this situation? Fourier transform, but it's there is a better name. You take linear combinations of solutions at individual wells, and there's linear combinations called the Bloch waves, right? Physically, we also know what's going to happen to the energies, right? I mean, if there was a series of, say, one delta function, there is one energy level, right? If you take n delta functions, this all splits into the one energy band, right? So that's what theta vacua are. These are the Bloch waves of the winding numbers. Okay. All right. So we go back in here and continue. So we take basically theta vacuum as the sum over n, the exponent of minus n theta, and sum over all of them. Now, there is one very central part of this story that I can leave without much proving, that if you have one vacuum with a value n plus, and again, any gauge invariant operator sandwiched with another vacuum, not vacuum, a state with another winding number, that the difference can only be proportional to nu, where nu is by definition n plus minus n minus, and it's also the difference in the delta in the Chern-Simons numbers with some coefficient, and that's integer. Okay, so this property itself allows us to prove superselection. So if you take theta and this operator rho and theta prime, there will be exponential factors that you combine these ends in terms of the sum and the difference. Okay.
So can you explain the notation? What's the vacuum expectation value?
Nu. So the result can depend only on nu. Right, that's what. So it's not going to be dependent on n plus squared plus n minus squared or something like that, right? But it's going to depend only on the difference between the winding numbers. Okay, that is feeds into the superselection rule, because you can now go through the quick calculation and convince yourself that the following is true. So this would be like morally, and plus and minus over 2. And here is the exponent of, another sum of nu, the exponent of I nu over 2. Theta prime plus theta, and the expectation value that depends only on theta, on eta, on nu, sorry. Very well. So the point is that nothing over here depends independent of n. So you can take this sum and arrive at 2 pi delta function of theta minus theta prime times sum over nu, the exponent of I nu theta. Because it's a delta function here, I can put theta equals to theta 1 and cancel this too, of theta. Or expectation value depending on nu. So we get the delta function as advertised. This is a very important property. So it's called super selection again. And the most important thing of it is not its infinity when theta equals to theta prime, because who cares? It's a functional integral. Many things go to infinity there. It's important that it's 0 and they're not coincident, right? Because that means that the transitions between different theta vacua cannot occur. All right, this is all very may look very abstract. Now we are going to go and right. So the basic end result, which you can lift this into the action by writing the in the functional integral, writing something like the delta function of nu minus g squared of 32 pi squared g duo, and in the action you write d for x, LQCD plus this theta term. All right. So therefore, we could, in principle, treat QCD as not referring anymore to the states with a finite winding number, but only work with the quasi-momentum theta that labels all the vacua. Now, after this formal discussion, what we'd like to do is to derive the mass of the axions, or the energy of the theta vacuum, and that would be the next exercise. Okay. Who has taken field theory where these things were explained? A little bit. So there are good reviews. What I should emphasize: this is a non-trivial corner of already non-trivial science, which QCD is, right? So this is exclusively non-perturbative effects. You cannot take a theta and draw it as a cross on the two wavy lines of gluons. You'll get 0 automatically. The same as for the photons, right? So because you will find that there is not enough momenta to contract your epsilon and polarization tensor. So theta has no non-perturbative interpretations. Okay. All right. So now we're going to do something closer to the real world, and before I do that calculation, I'll probably write an anomaly equation. So very famously, axial vector current that is going to be naively conserved in massless for massless quarks. It's actually not conserved, and the answer is proportional to the same notorious operator GG2. What it actually means is that if you take the quark field and you rotate it by an angle theta q with gamma 5, then in the action, or in a Lagrangian, theta will receive an addition, because of that term over here, will receive an addition of 2 theta q. Okay? That's an exercise that I leave it for you to do. There is a normal equation that basically connects the divergence of the axial vector current with GG dual operator. This is a anomaly term, just a regular triangular anomaly, and a mass term. Even in massless case, there is this. So if I transform quarks to chirally this way, then there is a theta term in the Lagrangian. Because of that relation, will rotate by that much. Okay. So based on this, we're going to perform a calculation of the energy of the well, you can call it energy of the vacuum, but it's the same as the mass of the axion at some point going to be. And basically, we'll start from standard part with its with the kinetic terms of the QCD. Then I'll take the two NF equals 2. Okay, so that our description is more compact. So I'll have mu u bar u minus md d bar d. And I have also g squared over 32 pi squared theta g dual. By the way, over here, I forgot to mention that in the Standard Model, or in any extension of it, the observable value, because of this actually, is the theta bar, which equals to theta QCD that we discussed so far, plus argument of the determinant of mu and md. That is, if you have written a gamma 5 mass for any of the quarks, it effectively, you can rotate it and put it back to the theta term. Okay. All right. So here is the starting point, and what I'm going to do is the following. There's a big secret that the energy of the theta vacuum and the mass of the axion is derived in the following way. You have an answer that is equal to 0. You split it into two parts, constant part and minus the constant part, and then you kill the minus constant from some arguments. And it sounds really silly, but that's what it really happens. The constant part that is killed by the mass of the eta prime that gets heavy through the instanton effects. No matter what kills the eta prime mass, makes the energy of the vacuum dependent on theta. Okay. All right. So what you do then? The literature is full of kind of awkward chiral rotations. People say, "Oh, let's rotate by this angle," and then they get the answer that is mixing with the pi, and they say, "Oh, let's rotate it again." So we're going to do the rotations that are really going to give us right away the desired results. So let's introduce the following: the rotation angle of the u quark that I'm going to use as m star over mu theta, and the rotation of the d quark is m star over md theta, and m star by definition, I take mu md over mu plus md. So these are like parallel resistors formula, right? Which it is. Okay. So when we do this, theta will rotate to theta plus 2 of these guys, which is equal to 0, right? Because we get, as everyone can see that it's equal to 0, that this is equal to 0. Now, that comes from this kinetic part of this, with which we rotate under this gamma 5 rotation, and because of that normally it kills this term. All right. So now, what happens with the masses of quarks? So with the masses of quarks, you can basically, if you perform this rotation, let me, since the time is short, I will just give you an upshot, and you can do it at home. So mass terms will become basically there would be minus mu u bar u cosine of 2 theta u minus md d bar d cosine of 2 theta d, and there will be a gamma 5 term that will contain minus mu sine 2 theta u bar I gamma 5 u, and then minus md d bar I gamma 5 d, and then sine 2 theta d. At that point, we'll expand through the 0, first, and second order in theta. Okay.
After you choose this rotation,
I can choose whichever I like, right? These are equivalent transformations in the Lagrangian, right? It's a unitary transformation. I'm a master of my domain and choose to rotate it that way. You'll see the benefit of it in a second. So expanding, what do we get? So expanding, we get the following answer. We get, of course, the zero order term, our original. So expanding to theta 1, theta, and theta squared terms. Okay, we get normal mass terms. Of course, what else? Then in the first order, we get basically, notice here there is mu, and the rotation angle is proportional theta u to 1 over mu. That cancels. So the gamma 5 terms becomes nicely 2m star. I don't even follow the sign because it's not going to be super important for me. But in the second term, it will be. Notice that this is singlet, flavor singlet combination. Okay. Now the theta squared terms. Okay. The theta squared terms, I will. At first sight, they give you no pleasure. There would be like m star squared over mu squared terms and things like that. So what you do, you split them into the u bar u plus d bar d and u bar u minus d bar d. So you have then plus 1/2 m star squared 1/2 m 1 over mu plus 1 over md, and then u bar u plus d bar d. So one term that you get, plus 1/2 m star squared 1 over mu minus 1 over md. And then here is u bar u minus d bar d. And what do I miss? Important term, theta squared in both. Okay. Now we are almost ready to read off the sort of quadratic term that corresponds to the basically curvature of that thing with respect to the theta squared term. Okay. So thankfully, as we all know, there is and if I go to the axiom instead of theta, I should be writing theta plus a over fa squared, right? Instead of with axioms, I should be writing everywhere theta plus a over fa, right? And I can even rotate the value of the a term, right? A parameter, because that's my choice, and I count it from 0, right? Absorb theta into the definition of a. Could do that too, right? Now, what do we see now? Well, we know one thing in the QCD, that q bar q is pretty much the same for both flavors, and it's approximately minus 250 MeV cubed. That is, of course, related to the mass of the pi and f pi by the following relation that is called I think it's Gell-Mann-Oakes maybe relation, I think. So that by itself should give us some joy, because we can read off the mass of the so this term we should be identifying with 1/2 ma squared a squared, right? That's the mass of the axiom that we're going to get. This term will give us gives zero because of u bar u is approximately d bar d. But in principle, you can keep it. This term nicely gives us identification that ma squared is equal to 1/2, and then this 1 over mu plus 1 over md is 1 over m star, right? As you can see from the definition. So I have 1/2 m star. Then I have minus 2 q bar, because that's what I just said. And this whole thing I can happily rewrite as and divided by fa squared, because that's where fa squared sits. And this whole thing I can happily rewrite as f pi squared m pi squared over fa squared. And here I have m up, m down over m up plus m down. Squared. Correct? All right. So that's a definition that you'll see in the derivation in many places. it sweeps one super important thing under the rug. What is it? No, we can generalize it to 3 quarks. Not a problem. There is one important thing. So let's assume that U1, contrary to the evidence we have in nature, that U1 symmetry is somehow realized in the meson sector, and the singlet of eta in this case would be as light as pions. What's going to happen is that this would induce A eta mixing. You say, well, what? Who cares, right? You get this diagram. There is a mixing. It propagates as eta. There is a mixing again, becomes A. So it's the same diagram in principle, right? And why do I kind of naively would say, oh, it doesn't matter. There is a mass of the quark standing in the vertex here. There is a mass of the quark standing in the vertex here. So this term is really, in the chiral perturbation theory, is the second order in the quark masses. I can throw it away as the quark masses go to infinity. However, don't forget that there is 1 minus m eta squared standing in the denominator here. So if eta were a gallstone, that this propagator would gain you one singular factor of mq. It will come to cancel that mq. And would you get constant minus exactly that constant, and you would get 0 in the limit of mass of eta going to the mass of pi. This thing is often glanced over, but it's a principal thing. How we can ever derive the mass of the axion or anything, right? Which with instantons and so on, when people have super much difficulty even simulating this on the lattice, we give like nice answer in terms of m pi squared, f pi squared, and the quark masses. And that is because the mass of the singlet is squared, right? Is much larger than the mass of the quark times lambda QCD. That's what it is. So it stays constant in the chiral limit, and therefore this term remains constant, and in the chiral limit, the second term does not contribute.
Really meant eta prime, not eta.
Since I've worked in the two case of right, if in the full QCD, it's eta prime, okay. Right? So since I'm working in the limit of two flavors, it's really eta. One thing that rarely makes into the particle physics books is that the U1, the heaviness of the U1 boson, is also a necessary condition for such a fundamental symmetry as an isospin symmetry. Because m up is not equal to m down by a huge lot, right? And if eta prime were among the pions, right, or in etas, the SU3 will be broken like 100% in nature, right? And if we stay in the regime of normal two-dimensional flavors, the isospin symmetry works because the mass of the eta is so much heavier than the mass of the pions. That's very rarely emphasized in particle physics books. All right, so we have derived the mass of the axion. That's the one. I hope everything is fine, right? So you can see that this is proportional to the quark mass, and this thing is proportional to the basically. That's right. So sorry, this is proportional to the ratio of m up and down. This is proportional to the mass of quarks times the lambda QCD cube over FA squared, right? Hence, this estimate, if you take a square root, that's the estimate I had on the blackboard in the summary. Any questions here? All right. So using the very same transformations and the well, I'm now going to drift to phenomenology and the charges, now physical, electromagnetic charges of up and down. You can see that in this model. You can see that in this model, there will be a coupling of A to F mu squared with a coefficient proportional to E squared over 16 pi squared, and 4md plus mu, F mu dual, where this is photon field strength. Over 3 mu plus md. If mu is 1/2 of md, this factor is 1. All right, a lot of phenomenological applications of axions sit on this type of coupling, and also on possible couplings to electron spin and quark spins, which all a little bit dependent on the way I would UV complete the axion model.
You just write down this as based on phenomenology.
This coupling follows from the model where I have G mu dual, but on top of this, there could be some additional model-dependent constant. Okay. So if I specify a UV completion, usually you have these things determined, right? But it's very hard to make inferences about 10 to the 9 GeV, right? Unless you are sure that your model is damn right? Then maybe, right? So, what's that? Yes, A over FA. Yes, thank you. Very well. So, in the remaining 5 or so minutes, let's discuss the UV completions of these things. This is being all nice sailing so far, but let's understand how we can get this effective field theory that will give us only the derivative couplings, shift symmetry, apart from the coupling to the GG dual. I have. Oh, I went over time. I'm sorry. You're right. I, for whatever reason, saw that until 15. Yes, thank you. That's the end of the lecture then. Sorry about that. Yeah.
Maxim, I heard this claim that